Thanks for having me.
Next up is Kyle Haustveit with Devon Energy. Are you there and ready to go, Kyle? You are.
Ready.
So I'll let you introduce yourself and get started there.
Kyle Haustveit, I'm 2013 grad, bachelor's in petroleum, and graduated last year from OU with a executive MBA in energy. Been with Devon's both summer internships and right out of school. Went through the normal rotational program and then landed in completions. And today I'm sitting in a centralized group that's helping all of our assets. I'm a geoscience manager, so we're working as an integrated team. We deploy diagnostics really focused on optimizing completion design, spacing, development decisions. I'd like to thank Dave for reaching out and just getting to stay plugged into Montana Tech it's a blessing. I'm thankful to be a graduate from a great school. Like Todd said, it's painful for the alumni to hear about what's going on up there. We're hopeful that we can be part of the solution, help with the mini or the externships. I know that email's been out, so I'd just like to remind the rest of the alumni on the call, look for opportunities to help our future fellow alumni out. Let's give them a chance to gain that experience and get some exposure to the industry. All right, so shifting gears, I'm going to cover a topic that we presented at the FRAC conference last year. It's a technique that we've used to improve our fracture characterization. So we're trying to gain more measurements at a lower cost and understand how changes to near wellbore strategies, perf architecture, rate changes, proppant size changes, how are all these things impacting how our fractures are growing in the far field? At the end of the day, for a completion engineer, we want to place the most economic design on a well. Normally that means we want to place our sand where it's meant to be placed, evenly distributing that fluid and sand across the lateral, across multiple clusters. So the title is Monitoring the Pulse of a Well Through Sealed Wellbore Pressure Monitoring, a Breakthrough Diagnostic. Before I jump in, I want to show a list. Lots of folks have been involved. I mentioned we work as part of an integrated team. A lot of these solutions cannot come out of one discipline. It's critical that we work together with our geologists, our geophysicists, reservoir engineers to really frame up the problem so we can develop the optimal solution.
Excuse me, Kyle, are you sharing your screen?
Oh, I'm glad you did it not come through. Seeing it now, Calvin?
Perfect. Coming. It's coming. Still black. Waiting for it.
Okay, I'll hold off till you give me the thumbs up.
It says something about double click to enter full screen mode. There it comes. There you got it.
Appreciate you letting me know, Calvin. Long list of authors here, lots of folks who are still with Devon, a handful who are no longer. Like Todd said, we've all felt the pain of the price war coupled with COVID. So just want to make sure the larger team is getting the recognition. So a quick overview of what we'll talk about. We'll look at the background of sealed wellbore pressure monitoring, how it came to be, the discovery, and then we'll look at a handful of diagnostics that we've used to cross-validate and wrap up with some conclusions. You'll see SWPM throughout the presentation. That's the acronym for sealed wellbore pressure monitoring. And a bunch of engineers came up with it, so the name's not very unique. It really is what the name is. We have a sealed wellbore, and we're using it to monitor pressure as we frack an offset well. The easiest analog I like to use is imagine putting a pressure gauge on top of a water bottle full of water and squeezing that water bottle. As you compress that system of nearly incompressible fluid, even a small reduction in volume is going to be a large pressure response. Because of that, using a new wellbore, we can simply place a surface gauge on a wellhead, which is very low cost and virtually no operational risk. The responses that we're monitoring are a result of a hydraulic fracture intersecting the wellbore and applying that compression to the system. The cornerstone diagnostic that we used to cross-validate was strain monitoring with permanent downhole fiber. We've also used downhole cameras and microseismic to validate. An important note is sealed wellbore is almost always used without fiber optics. That's what makes it cost-effective and scalable. We've used surface gauges for more than 90% of the stages that we've monitored. We have monitored with downhole, and there's some quality benefits to downhole gauges. And about a month ago, we finally received the notice on the patent that has been granted. Okay, so a little background story of discovery. We were not searching for sealed wellbore pressure monitoring. The discovery came as part of a large integrated diagnostic project where we had a treatment well. On the bottom, you can see there, treatment well in green with fractures extending away from it. And we had an offset monitor well. That monitor well was a new drill, not yet completed, and it had permanent fiber strapped to the outside of the casing, cemented in place, and permanent bottom hole pressure gauges. The pressure gauges are dual sensing, meaning that they're still on the outside of the casing, but one gauge is ported to measure pressure inside the casing. One gauge is ported to measure reservoir pressure. Our goal was to use the pressure gauge ported externally to compare and contrast the pressure responses we see to the fiber optic responses. We never intended to use the pressure gauges ported inside the casing for anything to do with offset pressure. And that's because the wellbore was fully sealed. So we didn't think that it was going to see anything. We were planning to use the internally ported gauges for some of the friction reducer testing on the frac, to measure pressure differential across the plug, and then to perform production and pressure interference testing post completion. But after monitoring this pressure, these gauges were permanent, so we were recording the data throughout the entire completion. There were 20 wells in this package, so I'm just showing 2 of them, but there were 20 wells in this package. And the first person to recognize that the internal pressure gauges on a fully sealed wellbore were generating responses was Wolfgang D. He was an engineer at Devon at the time. So we sat down and started kind of brainstorming and trying to decide what could this pressure response be related to. We shelved it for about a month, and then we came back and we looked at the fiber again. So we're digging into this large diagnostic with microseismic and tracer and interference testing. We look back at the strain data from fiber, and we compared the strain data to the sealed wellbore pressure data, and that was the aha moment. We saw a really nice alignment, consistent strain arrivals at the same time we'd see a pressure inflection. Before we dive into the image that compares pressure and strain, I want to get a little background on strain rate. Strain rate is measured on a fiber optic cable. This can be a permanent install like we had, or it can be a dip-in cable. With fiber optic monitoring, you're interrogating the fiber. That simply means you're shooting a light pulse down the glass cable. It's a very similar makeup to what we use in telecommunications. So the speed in which the light pulse comes back to the surface is the speed of light divided by 2. So that's why we're able to get tens of thousands of measurements per second. And the entire cable is the sensor. That's what's unique about fiber optics, is the entire cable from surface to downhole is the sensor. And as we interrogate that and things change in the cable, the way the light backscatters also changes. We're looking at the bottom, we've got a no strain rate change on the far left. So that means that our fiber optic cable, the glass cable, is staying consistent in diameter. The middle image is a fracture opening. So now imagine a fracture, which is growing from an offset well and intersecting a monitor well in the far field. As that fracture intersects that cable, it's creating an aperture. There's an opening. And when it opens, I think of it as a rubber band, and we stretch it. So when you stretch that fiber optic cable, it narrows the diameter and you get a very different backscatter signature. In order to create an opening in a rock, you have to have compression on both sides of that opening. So when you compress the cable, you're shortening it and you're increasing the diameter. So that's going to also change the light backscatter, but in a different way. So we look for this signature where we have a blue, red, blue, or compressing and then tension and then compressing signature. So that's our key indicator of a new fracture arrival at the monitor well. After we stop pumping or a fracture stops growing, we see a polarity flip, and where we had tension suggesting opening, we see it flip back to compressing or closing. So now we'll look at 2 stages of the completion, monitoring strain and sealed wellbore from the offset. This was the aha moment. This was the setup. On the left side of the image on top, we have depth increasing from top to bottom and time increasing from left to right. We're looking at 2 stages, so we can see a shift in depth. That's because we completed one stage, we moved back up hole and completed the next stage. So we're shallowing in measured depth as we complete each stage. We just walk through what the colors mean. So red is tension, fracture arrives, and we can see multiple arrivals throughout these 2 stages being completed. The diamonds on the left represent where clusters have been shot in each stage. They're colored by stage, so the white triangles are the stage 1 clusters. On bottom, we have our treatment pressure data, pressure and rate on the top. We had changes in our rate during the pump schedule. Here's a wireline pump down and then the second stage. Below that, we have our offset sealed wellbore pressure monitoring, and this pressure is being measured from the same well that the fiber optic is strapped to. Below that, we have the derivative, first derivative of the sealed wellbore pressure, and we use that to amplify these inflections. And then we can use an auto picker, use some pretty simple logic to look for peaks and troughs. Here we can see this is that first correlation that we really, sorry about that, the first correlation we look for. As soon as that fracture arrives, we see the blue, red, blue on the strain. We also see our first pressure inflection on the sealed wellbore. We can see a second arrival, a second inflection, a second fracture arrival, added deformation to the system. We can see an inflection on pressure and a second fracture on strain. We cycle our rate there, and one of those 2 fractures stops growing, and we actually see less deformation, 1 less fractures pushing on the wellbore. After the stage is completed, we pump wireline down to set the plug and shoot guns for the next stage, and we can see we reactivate 2 of the clusters from the previous stage. We actually see that on the sealed wellbore. It's not as large of a magnitude, but we're only pumping in at around 15 to 20 barrels a minute. What we see is a slight flattening on the sealed wellbore pressure. We see a pretty noticeable change in the derivative. Jumping to the next stage, very similar story. First fracture arrival on strain shows a clear indication on the sealed wellbore. Second arrival later in the stage, we see a second inflection. And again, the wireline pump down shows up both on strain and on the sealed wellbore. So this was the aha. We were excited. We believed what the pressure was telling us, and we knew that this was a pathway to a lower cost, more scalable solution to monitor far field fracture growth. Very simply, we look for uniform distribution. Our goal is to create fractures that are the same size, so we have the same SRV shape, and we can effectively drain the resource in place. So the metric we use is called volume to first response. It's simply the slurry volume we pump into a treatment well when we record the first pressure response on the offset. If we're distributing that fluid evenly across the stage, it's going to take more volume for each fracture to arrive at the offset well. If we're distributing that fluid in a way that's non-uniform, we'll have a runaway fracture that grows more rapidly than the other ones, and we'll see a very low volume pumped before the first response arrives. Perforation imaging is a tool that we like to use to measure the amount of erosion at each perforation, and we do that to understand how much sand exited that perforation. Again, our goal is to create uniformity, and one of the ways we do that is by trying to keep our perforation hole size similar across every cluster. Perf friction is a function of diameter to the 4th power, so maintaining an equal hole size is very critical to do that. The plot on the right is showing total perforation area for each stage. So each point is a total area measured from one stage. They're sized and colored by perforation friction, using the orifice equation to calculate perf friction. We have a larger area on top, smaller area on bottom, and the x-axis is volume to first response. So our goal again is to push that to the right. We want a higher volume pump before we see a response. And the main takeaway here is higher perforation friction, the larger, lighter colored dots, are correlated to a higher volume to first response. So this was an early indication for us that perforation friction is helping to improve our fluid distribution and The camera results agree very well with the sealed wellbore data. So again, cross-validating diagnostics is a very important step. Gauge comparison. There's a lot of offset pressure techniques that are commercially available. They've been improving rapidly over the last several years. So I wanted to compare two of the main types. Sealed wellbore is the first one, and then we'll look at an offset pressure below that. So with sealed wellbore, a single treatment or single stage being treated, treating pressure on the top. Below that, we have the smooth red curve is a sealed wellbore pressure on the offset with strain behind it. We see very nice alignment when that fracture arrives, pressure and flex. I mentioned we also had external gauges on the same well. So same stage, same location. Let's see what the external gauge looks like. Well, in this case, we had pre-existing fractures behind us, below us. And as we started to propagate and grow a new fracture from a new stage, it starts to compress the pre-existing fracture. So the result is if we're only using an external gauge, we see that pressure inflection much earlier, and it's not an indicator of a new fracture arrival. It's an indicator of a stress shadowing or squeezing of our pre-existing fractures. So this is a really important comparison. We can't use the external gauge in the same way that we can internal. Quickly, the next one is how much data can you get from a single well with the three main buckets of offset pressure monitoring? So the three buckets are sealed wellbore pressure monitoring, an external gauge like we looked at, or a newly completed stage in a child or infill well. And then the third bucket is a parent well or a primary depleted well. With sealed wellbore, the first thing I'd ask you to look at is the y-axis. On the second lane, our range is 1 psi. These are small magnitudes, but they're consistent. It's not a function of where the fractures intersect in the wellbore. It's whether or not it's squeezing that system. So very consistent arrivals. The next one is that external gauge, which behaves the same way as a newly completed stage. Now this y-axis varies by about 1700 psi. This is heavily influenced by how far away the fractures are from one another that you're monitoring from and creating. And then a fully completed lateral or primary well, much more variable because we don't really have any control as to where that fracture could be intersecting the monitor wellbore. And we risk screening out or plugging up that primary well, which happens here. There's a 1500 psi increase in the monitor pressure, and then we see it go on a fall off. And that's because we bridge that lateral with sand during the interaction. We were fortunate to work with another operator, so we've commercialized this technique. It's patented, and because of our partnership with Well Data Labs, they're able to sell it to other companies. We price it in a way that Devin can receive additional data to learn faster. We also give the operator the choice to pay a little more and keep it tight hole. This operator wanted to work closely with us, so they completed a fiber well, permanent fiber on one well, and monitored an offset well, also with permanent fiber. One of the main questions we got early on was, does volume to first response really correlate to the near wellbore distribution? So this is the best case study we had. We're fracturing a fiber well, monitoring a fiber well that also had a downhole pressure gauge and a sealed wellbore pressure monitor on it. The green line, this is the sealed wellbore, what we call uniformity index, and it's simply the volume to first response divided by the cluster count. The idea being, if you add more clusters, and you're truly treating those new clusters, this line should be completely horizontal. But if you add more clusters and you're unable to treat the additional clusters, you'll start to see that degrade over time. The blue line on the primary y-axis is the DAS, or distributed acoustic sensing. That's the measurement from the permanent fiber that we're stimulating, the DAS uniformity index, and we see the same signature. So as we add more clusters, we know it becomes more difficult to treat that full segment of that stage because rock properties are changing. We have more variability in our perf design. We have more pipe to cover. So we've seen historically, the more clusters that you have inside your stage, the more difficult it is to have uniformity. The x-axis is showing the number of clusters in the stage test that we had. So the highest count of clusters was at 7. They tested 14 clusters, 18 and 22. So strong corroboration between the two. Again, sealed wellbore, a fraction of the cost, aligned very well with what we were seeing on both near wellbore and far field fiber. Some problem statements, this is working with an integrated group again. Completion designs are almost always unchanged across the laterals. I'm pretty confident in saying at least 90% of the stages completed in the US are consistent, geometric cluster spacing, same pump schedule across 2+ mile laterals, but we know rock properties change. We know we have faults and features. We know we have variable cluster efficiency for a lot of reasons. Plug slip, poor cement isolation, runaway perfs, and to date, monitoring far field pressures and growth rates have been expensive and very difficult to do in real time. So for us, the problem was pretty clear, and we knew we needed a real-time solution to optimize completions on the fly. So some of the other diagnostics that have tried to do this, we have offset pressure monitoring from a fractured stage, which we've used and gained a lot of value from. The biggest con for us is it's been tough to scale. As we move into execution mode and optimization mode, we don't want any hiccups in the execution of these jobs. We've been putting 20+ hour pump days away and trying to alter the zipper order and staggering our completion can hurt those efficiencies pretty quickly. Cross-well strain, we've looked at a couple of examples. So one of my favorite techniques, it's very accurate. It tells you when and where, how many fractures arrive at an offset. The con is it's costly, and it gives you a single point measurement at one wellbore. Microseismic, the pro, very large coverage area, helps you understand what's going on between wellbores, how you're interacting with faults. The con is the cost can get high depending on the duration of monitoring, and the accuracy can be challenged in certain formations. Sealed wellbore, again, it's low cost, it's scalable, we know it's accurate, it aligns with strain. The biggest con is you have to have a sealed wellbore. So you need to delay prepping an offset well. Some of the use cases, cluster efficiency. So we rank by volume to first response. We'll add clusters, add perf friction, vary rates or fluids, and we're trying to improve how we place that fluid. And we've used this in real time. Last summer, we executed a handful of stages in Wyoming in the Turner Formation, and we made changes on the fly based on these responses. That resulted in about 10% on the completions cost savings on that well. We applied that new pump schedule to the next well and saved about $250,000 without sacrificing performance. Depending on how our well bores are spaced relative to one another, we can determine the hydraulic half length, insight into height. If we have a pinpoint completion, whether that's a single cluster in a plug and perf or a sleeve design, we can use that volume balance equation to estimate our fracture or hydraulic height. We can see how many fractures are generated in the far field. So we can actually see multiple inflections like we looked at that first case study. We've used it quite a few times to understand the impacts of depletion. So if you're drilling and completing a well next to depletion, is that depletion pulling your completion back towards the lower pressure sink? If so, how do you overcome that? Is it a recharge? Is it a refrac? Can you do anything to your new completion to try to limit that? And last, definitely not least, is fracture model or just a subsurface model calibration. So we use that to improve our certainty in our simulations. For a long time, frac models are calibrated using logs and DFIFs, which is great. Get a pressure match, things look good. This is just giving you one more step, one more level of confidence by saying, I know my pressure match is right, but I also know my hydraulic geometry is right at some distance, at some volume during that schedule. To date, we've monitored a little over 6,000 stages. The only gap for unconventionals in North America that we have to date is in the Haynesville. We've got one on the schedule. We've had the chance to work with 13 other operators, so including Devon, it's been performed for 14 operators in 11 basins on 180 wells. And since we published in 2020, you can see the uptake has been really great. Our commercial partner has been helpful in expanding this. They've got a wide reach, and we're learning a lot. I'd say, going back to what Deb said, networking is key for a lot of things. When we decided to share this technique externally, because of the networking and involvement with SPE, I was able to reach out to key people before we published it and spend some very important time with small groups, one-on-one, and talk through this technique, understand the need in the industry, and get some valuable feedback that helped this, I believe, be a lot more successful than it would have been if we hadn't been working with others. The other benefit to us is we get to learn a lot faster from a lot of smart people. Realizing there's other resources out there is very important. You learn a lot faster together than you will in a silo inside one company. So quickly, in closing, it's a low-cost diagnostic tool. it's a really interesting process to go through the discovery to the IP process to the commercialization process, and ensuring that you're realizing value, you're protecting value every step of the way. Extensive validation, a lot of diagnostics and case study across almost every US basin. It's a measurement of hydraulic geometry. It doesn't need to interfere with zipper operations, and you can see the case studies below there. So with that, again, acknowledgements, lots of folks have been involved. And I'll stop there and open it up for any questions.
Great. That was a real interesting presentation. Thanks, Kyle. Are there any questions for Kyle real quick? Got a few minutes. So I got a couple quick comments on here. One, I really appreciated that you weren't initially looking for this. You're developing some tests to look at some other stuff, but because you're looking at everything and paying attention to things, you saw this response and were able to use it. I think that was a neat way to kind of develop the technology there. The other thing, I like that you mentioned the networking and how that helped you develop your technology. That really kind of tied in with what Deb had to say as well. It was good job, and I appreciate it. Any other questions for Kyle?
Hey, Kyle, this is Greg Hilton. Can you hear me?
Yes, sir.
Yeah. I was curious what you saw on that well related to volume to first response that made you make the adjustment. Did you actually not see a VFR, and that's why you either lengthened your stage or reduced clusters? What was it?
Yeah, good question. And really, this first trial was to see, can we do it? There's some delay in data transfer from field to the office. So number one goal was, can we see a response in time to make a change that has a cost impact? And can we communicate that back to our consultants in the field to make that change? So that was really the focus. Luckily, in that Turner formation at that well spacing, we had quite a bit of data. So we had a statistical understanding of what the range should be for volume to first response. So we took our P50. Very simply, we said, if the response is less than our P50 and the well's treating favorably, we're going to go ahead and tell our consultants that they can place the rest of the design proppant with as little fluid as possible. So we allowed them to start ramping prop con, ramping rate, and that's how we were able to realize the cost savings. Most of our frac crews are on time-based contracts, so we saved on the time on the crew and then the cost of water and chemicals. There's a lot more that can be done on real-time completions, from changing rate to diversion to prop size to fluid viscosity. There's a lot of things that haven't been studied enough yet, but for us, it was simply a test first and foremost. Can we even make a change in time to have a cost impact?
Okay, great, Kyle. Thanks, great presentation.
Thanks. Thanks for the question, Greg.
Any other questions for Kyle? Todd?
Yeah, so can you tell how hard you're being hit by the magnitude of your pressure, or you can only tell kind of from your volume to first response?
Great question. It's very high on our development list. We've seen, well, luckily we had a setup one time with a downhole gauge and we didn't have fluid to surface. And what that allowed us to do was to quantify the amount of deformation. Because if you don't have fluid to surface and you're measuring your pressure in the bottom hole, when you compress that system, the delta P is a function of a hydrostatic change. Right? We know our ID of the pipe, we know the height of that column, we can calculate the volume of deformation. So Todd, it's a function of two things we believe. It's a function of the net pressure in the formation and the number of fractures causing the deformation. So it's a very important QC check for us to know that, because you can imagine if we've got 3-4 wells zippering, sometimes 2 crews going, we need to make sure we can differentiate a new fracture arrival from a wireline pump down. So we can use that magnitude as a very important QC process, but then also additional insight into how many fractures are intersecting that monitor well.
Just to be clear, you can today measure that, or that's what you're planning to do in the near future?
We can, but I'm confident we haven't squeezed out all the information that's inside of the magnitude.
Awesome. Great man. That's fantastic work, Kyle. I really, really enjoyed the presentation.
Thank you.
Kyle, I think there's a quick question in the chat box for you, if you look.
let's see here.
from
Let's
R1?
There's a couple.
Okay.
No issues with fiber cable dam. Oh, yeah, great question. So when you're fracturing a permanent fiber well, we map the fiber. We use a USIT, and we use that USIT to map where the fiber's at. We use a mag tool to also understand where that cable is, and then we orient our perforating guns away from it. So knock on wood, to date with Devon operated fibers, we haven't cut or shot fiber. If you have a leak from isolating packers or sensors. So on the leak question, we don't run packers, and 99% of the stages we monitor are in brand new wells that have yet to be completed. No perforations or toe sleeves open, so there's no access to the wellbore. If 90% of the fractures stay almost the same, what is the room for improvement you target? Yeah, if we have 90% uniformity, I wouldn't change a whole lot. If I was that uniform, then I'd probably start stretching my stage out. I may add 2 or 3 clusters and try to stretch it and continue to improve. As we increase stage length, we can decrease costs. Are we able to quantify uplift in gas production versus sand placement? That's a great question. I think the biggest hole in diagnostics for unconventionals and horizontals is accurate production logs. So it's a difficult question. We do know that with improved distribution, overall well performance is improving. And even in the current environment where costs are the main focus, we've been able to stretch stages out, reduce costs, and maintain performance. So it depends on commodity price and what we're chasing, if it's costs or if we are really trying to get a lot of uplift in performance.
Okay, great. Thanks, Kyle. That was interesting.
Thank you.
Let's see, have you take your screen share down.